All right. So again, I got this recording now. And again, I'll post this recording into Canvas like I did with the last times. I didn't do the first times, and I kind of regret that. So anyway, I'll start recording the Zooms from here on, and they'll be on there, so you can go back and watch them. If you don't want to watch the whole thing, you can find specific parts. One thing I like, you can speed it up. So if you think I'm talking too slowly or you want to hurry up and get to something, you can speed it up. If I'm talking too fast, remember you can pause and replay it. Yeah. Or if you need me to repeat something, guess what? Rewind a little bit. There you go. Okay, so that's basically the review. So we're looking at 29 questions-ish for the test. And you're going to need to do that at some point next week. Again, Lebanon people, you guys are going to take it here on site during regular class time. If that's a problem and you need to have it proctored, I can probably make that happen. Just, I mean, that way it's universal across the board with man. It'll just be easier if you just come here and do it. Anyway, and then for you guys that are off-site, you'll need to do it proctored, or I guess, like I said, if you want to drive to Lebanon, or maybe you live in Lebanon and drive to Republic every week, that's, you know, it is what it is. All right, so we're going to start with 2.4, and I'm actually going to switch to a pen that I can see a little bit better. I can figure out where my pen went, but there we go. All right, and 2.4 covers two topics that are fairly similar, but it's going to be very different than anything we've done so far, at least in my mind. 2.4 is a lot of yes and no type of questions, okay? 2.4 covers symmetry, and then whether a function is even or odd, or I guess neither. And those are different but similar, and we'll discuss each, and kind of we'll do each one in three different ways. So the first one is symmetry with respect to the x-axis. And again, we're going to look at this in three different ways because they're going to ask you questions kind of involving all three. Mine will mostly be involved with the graphs. I like looking at it that way. So again, the x-axis is the horizontal axis. Y is your vertical, x is your horizontal. So we're looking for symmetry, okay, kind of like a mirrored reflection with respect to the x-axis. An example would look something like this. Okay, so if each point on the graph has a mirrored reflection, equidistant, so this would be the exact same distance from the x-axis. This would be the exact same distance from the x-axis. Okay? So basically, if you've got a mirrored reflection over the x-axis, that is symmetry with respect to x. I'll do another one. Okay? So if this graph is going in this way, symmetry with respect to x would look like a mirrored reflection. Basically, if you think of it this way too, if you could fold it in half over that, then you have symmetry with respect to x. And it could go opposite too, I guess, like it could go in that direction as well. So again, if each point has a reflection in the same location across from the x-axis, then you have symmetry. Yeah, so each point on the y would have a mirrored reflection that's equidistant from the x-axis. So again, if we could measure this and say that's 2 units, We measure this, and that's also 2 units, and it's that way for each point. Okay, then you have that symmetry. And if anything doesn't match up, then it does not have symmetry. So I'll do some counter examples. So these have symmetry with respect to x. So then these ones I'm going to draw over here will not. So this is going to be my counter examples. So say we've got a graph that kind of does this number. And again, with respect to the x-axis, if we folded this side of the graph down, or if we folded this side of the graph up, it should be up here kind of like this, but it's not. So there's no symmetry with respect to x-axis here, or here for that matter. Same thing, if I folded this one down, it should be over here. But there's no graph over here, so there is no symmetry with respect to x.
So you're just saying that you can fold it and make it symmetrical.
Correct.
It doesn't make it symmetrical.
Right, but you also have to, the question was, so as long as you fold it, then it's symmetrical. But that's also with respect specifically to the x-axis. So if you're looking at this graph, this one would have what we would call horizontal symmetry. So yes, this graph matches up here and here, but again, it's got to reflect over the x-axis. If we took this graph and folded it over the x, okay, it doesn't work. Our symmetry is for some arbitrary line up here, which doesn't help us. We're talking about specifically with respect to the x-axis. So again, this point right here needs to be able to reflect over the x-axis, which it clearly doesn't. So again, this one has no symmetry. Correct, these are both no's. And again, with respect to x, these do both have symmetries, but it's a different kind. So again, with respect to the x-axis, so specifically the horizontal axis of your graph, these two are both examples of yeses. These two are both examples of no's. Now, that's if they provide a graph, which on some of the problems they're just going to draw a graph, and they're going to say, hey, does this have symmetry to the x-axis? And you'll click yes, or you'll click no. It's simply a yes or no type of thing. Now, they could also ask you for a specific coordinate. If you have a specific coordinate, and you want to reflect it over the x-axis, that simply takes your y value and makes it negative. So so again, if we can kind of look where I'm pointing here, okay, this coordinate, when it reflects, the x value, the horizontal, doesn't change. What changes is the y. Okay, so same thing. Your x, your horizontal doesn't change, your vertical changes. So if you reflect it, it simply changes the sign of your y value. Positive 2 reflects to a negative 2. The x doesn't change. And again, when reflecting over the x-axis, we'll switch to the y-axis later. Okay, and that would work for any coordinate. So if we had -3, -4, and we want to reflect it over the x-axis, again, the -3 is going to stay, but the -4 would reflect to become a positive 4. So they can give you the graph and ask, does this have symmetry to X? They can give you a coordinate and say, does this have symmetry with respect to X? Sometimes they'll actually ask you to fill this one in. So it's like, hey, which coordinate would have symmetry with respect to the X-axis? And that would be just changing the sign of the Y. Correct. If they give you a function basically to figure out, does this have respect? Does this have symmetry with respect to the x-axis? What you do is you replace y with negative y and see if anything changes. If something changes, then no, there's no symmetry. But in this case, if we take negative y and square it, that's negative y times negative y. Negative times a negative is a positive. So basically plugging in negative y doesn't change anything. I still end up with the exact same function. Then this one does have symmetry with respect to x.
So why are the two negative y's near that one?
It's just showing negative y. So the question was, why did I write the two negative y's? I was just showing negative y squared is negative y times negative y. Yep. So that just shows negative times a negative, again, yield me the positive y squared. That's why the negative ended up going away.
Because it ended up the same, that's how you know it was.
Yeah, to answer that question. So yeah, as long as you end up with the exact same function, even if you plug in a negative y, the function doesn't change. That means you have symmetry. If your function does change, that would be a counterexample. So if we had, say, y equals negative x plus 4, if we replace y with negative y, and say I want to get y by itself, so I would have to divide by negative 1. And now I get y equals positive x plus negative 4. And that's not the same thing. Those are different. Negative x compared to positive x, positive 4 compared to negative 4. So this particular function would not have symmetry. So if you plug in negative y and you get a different function, then there is no symmetry with respect to x. If you plug in a negative y, but you still end up with the same function, then you do have symmetry.
Where did that negative one come from again?
I divided, so I needed to get this. So to see if I had the same function, I wanted to make my y positive again. So I replaced y with negative y. And then I wanted to see what happens if I make my y positive again. And again, it flips my function. To me, one thing that's going to make this a little less confusing is there's really only a couple of things that can make this function have symmetry. Basically, if you've got y to an even power, like a 2 or a 4 or a 6, and again, that's a power, not a multiplier, but a power, that will cause symmetry or absolute value. So for example, if I said, let's get a clean sheet of paper, okay, the absolute value of y plus x equals 2. Absolute value is these vertical bars. Absolute value takes whatever is inside of here and makes it positive. So if I plug in a negative y, the absolute value of a negative is a positive. So this and this would still be the same function. So this one would have symmetry with respect to x. So again, y's to even powers. Okay. Anything like this. So as long as your y's are all to even powers and there are no odd powers of y, these would have symmetry with respect to x. So that's kind of your key. So an absolute value of y or y's to all even powers. And they do have to all be even powers. So if I said y squared plus 3y plus x equals 0. Okay, the fact that I've got a y to the first power, that would make this not have symmetry. And again, this is all symmetry with respect to the x-axis. Okay, same concept, but we're going to change this up, and we're going to talk about symmetry with respect to the y-axis. And again, they're going to do all three things. They're going to give you a graph. They may give you a coordinate. They may give you a function. Just now we're talking about with respect to the vertical axis, the y-axis. Everything else basically stays the same. So you want to reflect it over the y. So if you can fold it horizontally and it matches up, then you have symmetry with respect to y. So this is an example of a yes, you have symmetry with respect to y. Okay, and again, as long as every single point matches up, again, equidistant through that y-axis, then yes, you have symmetry with respect to y. And again, don't confuse that for symmetry with respect to x, because this has symmetry with respect to x, but not with respect to y. So again, if you match this point over the y, there should be a point over here. There clearly is not. This function goes in this direction. Same thing, if we had something that looks like this, each point should reflect over the y-axis. This one clearly does not. So again, that's an example of one that does not have symmetry with respect to the y-axis.
Can you get your paper over?
Is that better?
A little bit further. Thank you.
Okay. It's centered up on my screen, so yeah, if you need me to adjust something, just let me know. Thank you. Now, again, if they give you a specific coordinate and you want to reflect over the y-axis, now the x is the one that is changing. and the y stays the same. So now we're staying the same vertically, we're just changing our position horizontally. So instead of 1, 2, now we're at negative 1, 2.
So it's just reversed if you choose that.
It is reversed, which is again where this is going to get confusing. The concept's not super difficult, but you got to make sure you're talking about the right one and answering the right question. Does that make sense? Very easy. It's very easy to make simple mistakes. And that's math. Just thinking negative signs and mother fractions. Okay, and the same way with your functions. If they give you a function if I can replace x with negative x, and I still get the same function, then it has symmetry with respect to y. So again, it's completely inverted from the other. Symmetry with respect to x was all about changing the y to a negative. Symmetry with respect to y, it's all about changing the x to a negative. And again, negative x squared means negative x times negative x, which will give me a positive x squared plus 1. So I end up with the exact same function. Nothing changed. So yes, this has symmetry with respect to y. And just like before, basically the only thing you can put a negative x in for and not change it is even powers of x or absolute values of x. Pretty much anything else is going to cause you to lose your symmetry. So again, if you have all even powers of x, x to the 4th plus x to the 6th, plus some number, or minus some number, or nothing at all, okay, you're good. As long as you have even powers of x, that would be an example of, yes, that has symmetry with respect to y. However, all it takes is one odd power, and you lose your symmetry. So this one would not have symmetry with respect to y. So again, even powers and absolute values. Again, and that's all that can be present. Once you have something else, then it's no longer got symmetry with respect to y.
So that's just an automatic.
It's automatic. That's pretty much the only thing that's going to make a negative x the same as a positive x. That's what causes all of these things to happen. When x is squared, that's what causes this curve. And x to the 4th causes all of these curves, and it all matches up nicely. And again, even if it, curves the right way, if it shifts in this direction, we lose our symmetry, and that's what this odd power would cause, okay? It would basically take this W function and would slide it one direction or the other, which again causes us to lose our symmetry. Because again, while we do have our, whoops, I keep covering it up with my hand. Okay, while we do have our symmetry here, it's not with respect specifically to the y axis. So again, this point has to be able to reflect over y, and it clearly doesn't. So that's why it's in the no category. We've got one more type of symmetry. That symmetry with respect to the origin. This is also called 180-degree rotational symmetry. And this is actually where it's going to be nice to do this on paper instead of on a dry erase board, because you can actually take it and turn it. So, and again, with respect to y and x, 180 degrees is, a half of a full circle. 360 would be to completely spin it around. If we can turn this 180 degrees and we still get the same picture, so this is going down and to the left, up to the right. If we actually physically rotate this 180 degrees, we still get the same picture. We go down and to the left and up and to the right. So if you can actually rotate it 180 degrees and you still maintain the same picture, then you have symmetry with respect to the origin. Same, we've kind of got a curve up here, going like that. We've got a curve down here. Now I'm drawing these by hand, so you got to pretend that these actually match up. The same thing, again, quite literally, you take this and we spin this 180 degrees, we still end up with the same picture. So we still have our curve in the top left and our curve in the bottom right. So again, if you can turn it 180 degrees and still maintain the same picture, then again, you have symmetry with respect to the origin. So a counterexample. Okay, we've got a parabola that's facing up. Again, we spin it 180 degrees. Now my parabola is facing down. That's no good. Let's see. Some funky we may see. Yeah. Okay, again, something like that. Flip it 180 degrees. We're pointing the completely wrong direction. We were facing to the right, now we're facing to the left. So again, and some people can picture this without having to flip it around, but these would be examples of not having symmetry with respect to the origin. Now again, this one has symmetry with respect to y. This one has symmetry with respect to x, so make sure you're paying attention to, again, specifically what we're looking for. In this case, it's with respect to the origin. And again, if they give us a specific coordinate, (180-degree rotational symmetry), we'll flip the signs of both. So if this is the 0.2, 1, then that's going to reflect to the point -2, -1. Or +1, +2 to -1, -2. Okay, so 180-degree rotational symmetry changes both sides. And if they give you a function, you would replace both y and x with negatives and then see if that changes your function. In this case, -y equals -1 over x. If I multiply everything by a -1, then I end up with a positive y and a positive 1 over x. So again, if you can change both of them and it doesn't change your function, then you do have symmetry with respect to the origin.
Now, do you always have to include the parentheses, or you just do that for example? Because sometimes I have parentheses.
Typically, whenever I multiply, I include the parentheses. Or if I'm substituting something, I use the parentheses. I always include it just to prevent confusion. Because with exponents, you have to. With negatives, you typically have to. So I'm going to say, yeah, you have to.
How does it end up positive again?
Because, all right, so we had -y equals 1 over -x. I want to see if I have the same function here, so I got to get my y back to positive. So to make a -y positive, you can multiply it by a -1, or technically you can divide by a -1. But we've got to do something to get this back to a positive y to see what happens over here and see if my functions match up.
So you just grab the one because you want it to?
Well, if I multiplied by a -2, that would change everything.
Right.
So I just want to see if my function changed. So I grab -1 simply to get rid of that negative. I wanted to get a positive y, and then I just wanted to see what happens over here. If I multiply by a -1 on the left, I also have to multiply by a -1 on the right. So technically I get -1 over -x, negative divided by a negative is a positive, which was my original function, so nothing changed. Now, again, on my math lab, they're just going to give you some graphs and they're going to ask you a question like, okay, whoa, there we are. Okay, so does this graph have any symmetry? So your choices are, does it have symmetry with respect to the x-axis? Does this have symmetry with respect to the y? Or does this have symmetry with respect to the origin? And again, x-axis, can we flip it horizontally over the x? I keep covering up my stuff. Hate being left-handed. If I flip it horizontally over the x-axis, is it a mirrored image? Okay, with respect to the y, if I flip it vertically over the y-axis, or I guess horizontally over the y-axis, over the vertical axis, okay, do I have symmetry? Or if I flip it over 180 degrees, do I have symmetry? And in this case, we have symmetry with respect to the y.
So there's no respect to the x-axis.
Not in that other one. So this particular graph has only symmetry with respect to the y. Now again, pretend that I can actually draw a decent function and say this all kind of matches up. So this is the same point here is here, the same point here is here, same point here Anyway, these curves are all exactly the same. Can't you tell by my beautiful artwork? Fair enough. So if we're looking at this particular function, can we flip it vertically over the x-axis and everything matches up? Yep. Can we flip it horizontally over the y and everything matches up? Yep. And if we take this guy and flip it 180 or rotate it 180 degrees, do we still have the same picture? Yep. So this particular graph actually has symmetry in respect to all three. This has symmetry with respect to the x, this way. You have symmetry with respect to the y, that would be this way. And you have that 180-degree rotational symmetry with respect to the origin. So you can have all three. Another good example of one that has all three, if you can pretend this is a perfect circle. A perfect circle centered at the origin will also have symmetry to all three. You flip vertically over the x, you flip horizontally over the y, or if you rotate it, all the same. Yep, the circle is yes to all three.
So is there going to be, so is it pretty much like any time there's a pattern, a circle or like that one good, kind of be a good clue that's going to be asked?
Yes and no, because the question was, so anytime there's like a kind of circular pattern, it's going to be to all three, and that's not necessarily true. Again, you can kind of pretend with me here. Say all of those match up. Again, that would have symmetry to all three, but that's not necessarily circular. Okay, so yes and no. Same thing if I draw my circle off-centered. Now that has nothing. That has actually no symmetry with respect to x-axis, y-axis, or origin. So this is none to all three. Nope, nope, nope. So even though it's circular, if it's not centered at the origin, we don't have any of our symmetries. The last concept for 2.4 is whether a function is even, odd, or neither. Trying to remember where I wrote that down. Can't find my stuff. I want to make sure I tell you the right thing. An even function, if we replace x with negative x, nothing's going to change. We're going to end up with the original function. If we plug in a negative x and we end up with a completely negative or the completely opposite function, that is an example of an odd function. Anything else would classify as one that would be neither. of those.
So is it the X that you're focusing on?
Correct. Yeah, even, odd, and neither is totally based off of your X values. And again, the only thing that can take a negative X and basically make it the same is, again, even powers of X or absolute values. So this is an example of an even function.
So on that even one,
Yep.
it has a negative X and a regular X.
Right. So if you plug in negative X, do you end up with the exact same thing you started with? Is what that's asking. So let me walk through that one a little better. So say f of x equals 3x squared plus 2. To check and see if this is even, I want to plug in negative x.
Oh, so that's just like a plug-in formula.
That's a plug-in formula. So then if I plug in negative x, does that really change anything? And in this case, no, because negative x to the second power is still going to be positive x squared. So I still end up with the exact same function. Nothing changed. So if I can plug in a negative x and nothing changes, that's an example of an even function. Okay. If I plug in a negative x, but I end up with the completely opposite, okay, same function, different sign. So if f of x equals 2x, if I plug in negative x, 2 times negative x is negative 2x. So I end up with a completely opposite function. This is an example of an odd function. And then anything else would be an example of a neither.
You do it over again.
Oh, sorry. Is that better? I do 3x plus 1. Again, if I plug in my negative x, so if I plug in negative x, 3 times negative x is a negative 3x plus 1. Really, neither of those things happened. I didn't end up with the exact same function. That would be positive 3x plus 1. Okay, so it's not even. But the opposite would be negative 3x minus 1. And I got a negative 3x plus 1. So this is neither even nor odd. This is a neither. It's just a function. It is not even or odd.
So is there a plug-in formula for neither?
Not for neither. For even, okay, you're going to have only even powers of x. Technically, for odd, you need only odd powers of x and no random constants. really the best way is to just literally check it. You're going to have to plug in your negative x and see if anything changes.
So you're still plugging in negative x on the even amount.
Correct.
You're just the same as the
Yeah. The even one, again, requires all even powers of x. Odds in neither, you really just have to plug in and check. The last section, 2.5, so this is the last thing we're going to talk about as far as this unit is concerned, deals with transformations. Transformations is literally just a sliding or a shifting of the graph. You're going to start out with a graph, and it's going to shift either left or right or up or down based off of some kind of parameter changes. So regardless of what the function looks like, okay, so you have some f of x, if you multiply a number or add or subtract a number within the function, or add or subtract a number outside of the function, each of those pieces, parameters, has an effect. It's going to shift your graph. A multiplier will stretch or shrink your graph. The bigger the number, the more it will stretch it vertically. The smaller the number, it will squish it. And again, I'll show you examples of all of these. I'm just going to kind of explain it all up front first, and then we'll actually do some concrete examples. Whereas your number inside of the function will shift your whole graph either to the left or to the right. And this one actually moves backwards to what you would think. So a negative number, so if we're subtracting, that's actually going to go to the right. And if you add a number, if there's a plus, that's actually going to shift it to the left, which remember is backwards. So on a traditional XY axis, okay, your positive numbers are over here and your negative numbers are over here, okay? So your shift left and right is actually backwards to that. So a plus number will actually shift you left and a negative number will actually shift you to the right. So this one's kind of backwards to what you would think. And then this number, K, is going to shift the whole thing up or down. And then this one moves just like it's supposed to. A positive is going to go up, and a negative is going to go down. And if this A value happens to be negative, that's going to flip your whole graph vertically. That says vertically. My handwriting is terrible. That says flip vertically. So again, these are your parameter changes, and I'm going to keep kind of coming back to this same equation, function, expression, however you want to say it. Because we're going to talk about some specific ones, and I'm going to show you how these shifts kind of occur. And then I'm going to actually show you some specific problems within my math lab and what it looks like and how to graph and those mechanics and stuff like that. So if I give you some function like x squared, a typical x squared function looks like a parabola. It's going to go like so. So if I take this function and I said we're going to do x plus 3 squared minus 1. So again, the x squared is my initial function. So this plus 3 is inside. That's the same as that h value. So the plus 3 inside of the squared. So see how the squared is here? The plus 3 is happening inside of that. That means it's happening inside of the function. So that's the same as that h value. Okay? This minus 1 outside of the function, outside of being squared, corresponds to the k value. We don't have a multiplier, so there's no a value. Well, our a value is 1. So if you don't see an a value, it's automatically a 1, and we did not stretch or shrink. That's going to be regular. So this is going to take my exact same graph, and it's going to shift it, okay? This plus 3, so a plus is actually going to shift us to the left. So this says we're going to go left 3 units. Okay, and then minus on the k shifts us down. So this minus 1 is actually going to shift us down 1 unit. So it's this exact same curve, but instead of this point being here, say at 0, 0, it's actually going to go to the left 3 and down 1. So that's basically the same as this point here. This point here at 0, 0 would go left 3 units and then down 1. So that's my new point. Those points would correspond. So from 0, 0, I would go left 3 and down 1. And each of these points would do that same thing. So this point here is at 1, 1. So from 1, 1, we would also go left 3, down 1. Kind of. It's kind of the same as slope. You're just, again, shifting your whole graph. So basically, if I could, like, on a computer, if I could, like, highlight this curve, grab it, shove it left and down. So I'm just going to take this same graph and I'm just going to grab it and shift it. That's what a transformation is. We're literally sliding our graph. So like if you picture the XY coordinates staying put, I'm just going to grab this curve and I'm going to shift it left and down. Yeah, and that's it. So that's all we're doing is you're looking at the numbers that we're doing here to the function and you're giving it a direction and a how many. Okay, so if they gave us a completely different function, okay, a square root of x, a square root of x function typically looks like this. Okay, we're going to do these changes. So again, square root of x represents my original function. So my question is, what are we doing to this? So now we've got a multiplier. We're not adding or subtracting anything outside. We have a multiplier. So this is the same as that a value. So that's going to stretch or shrink my graph. And this -1 being inside of the square root, okay, makes it an h. It's going to move it left or right. We're not adding anything outside, so we don't have a k. We're not moving this up or down. So this is going to stretch by a factor of 2. And then this -1 is going to shift us to the right 1 unit.
So is that squared going straight over taking the function of x minus 8?
No, there's no x minus 8. Oh yeah, okay. So this x -1 represents, yeah, an x minus h. Yeah, I see what you're saying. So again, if this is my original function, this is called the parent function. This is the parent graph. Okay, what we're going to do is we're going to take each of those points and we're going to shift them 1 unit to the right. Then stretching by a factor of 2 basically multiplies your y by 2. Okay, so again, think in terms of vertical. Y is vertical. Okay, so each point gets shifted to the right 1 unit. And then we multiply that y value. So this is on here. So this is a y value of 0. 0 times 2 is 0. So this one's just going to shift right 1 unit. Okay, this point here at 1, 1 is going to shift right 1. But now with a y value of 1, if we double that, okay, we're going to go up to 2. So this point went to here. This point is at 4, 2. So again, it's going to go right 1. And then we're going to multiply it. So a y value of 2, if we multiply that by 2, that gets us to 4. So 4, it's right there. So this is going to be my new function. It shifted every point to the right 1, and then it multiplied the y values by 2. You can kind of picture it. It took it and stretched it vertically. So again, this 2 stretched the vertical by double. Because this was on the x-axis, it didn't get stretched, but the rest of the graph stretches. So we went from kind of a flat curve to a much more stretched curve. And then this -1 shifted everything to the right 1 unit.
So in the stretch and shrink, how do you know when you stretch and shrink?
If there's an, okay, stretch and shrink, again, if there's an a value, you multiply a times your y. So again, your y is the vertical component. So each individual point, so if I could, if f of x equals square root of x, we're going to do this kind of point by point. Okay, so those are my coordinates. So this one is at 0, 0. This is at 1, 1. This one's at 4, 2. And again, we're going to take every single one of those points and we're going to shift them to the right 1 unit. And then we're essentially going to multiply the y value by my a value. So I'm going to take my y value times 2. So again, each individual point, so 0, 0.
The multiplication itself is with the size.
Correct. And you're stretching vertically, not horizontally. So you're always stretching the y. So again, 0, 0 comes right 1 unit. And again, looking at my y value is 0. So 2 times 0 is still 0. So this one's not going to move vertically. This is going to stay here. This point, this 1, 1, is going to shift to the right 1. And then again, my y value of 1, 2 times 1 is 2, so now I get a y value of 2. So this, again, 0, 1. So this is going to be the point. So we moved right 1, so that's going to become 2, 2. And again, the point 4, 2 shifted right 1, so that's going to be at 5. And my y value of 2 gets multiplied by 2. So then that's going to become the point 5 and 4. And if you look at those graphs, okay, kind of side by side, we shifted right 1 unit, and then we stretched the whole thing vertically. So again, if I can kind of lightly draw in what we had initially. Okay, that was my initial function. We shifted everything right 1 and then stretched it vertically. That's what that 2 does. So this shifts us right, this stretched it out.
And sometimes that multiplication will shrink it.
If it was a fraction. So if I multiplied by a half, you'd be cutting everything in half, so that's what would shrink it. So the bigger the number, the more it's going to stretch it. If we would have tripled it, it would be going way up here. If we would have cut it in half, okay, so the smaller the number, that's what's going to shrink it. We take this same function. I'm going to stick with the square root one.
So in the homework, there's going to be like
I'll show you exactly what it looks like. Some is going to be matching. Some they're going to ask you, actually want you to graph it, but you kind of do it with sliders, and I'll walk through step by step exactly what it's looking like and exactly what it's asking for. So again, initial function, square root of x, looks like this curve right here. We've got this negative, and again, this plus 2 inside of the function. So again, this plus 2 is going to shift us left 2 units. This negative is actually going to take my graph and it's going to flip it over vertically. So again, just redrawing the original function. So this is the old one. This is not my new one. I'm going to shift every single point left 2 units. So this point here at 0, 0 is going to shift left 2 units, and then it's going to flip over the x-axis. Now we're actually on the x-axis, so that one's not going to flip. Okay. This point here at 1, 1 is going to come back to the left 2, and then it is actually going to flip. So right now we're 1 unit above. We're going to flip to 1 unit below. So this is my new point down here. Same, this one's 2 units above, so we're going to go left 2, then we're going to flip to 2 units below. So this would be my new function.
and that's still connecting to the x squared.
Yeah, this is still based off of the initial function of the square root of x. So I graphed, so this is just the regular square root of x. And then this is the negative square root of x plus 2. So again, the negative is what caused it to go down instead of up. The plus 2 shifted everything left 2 units. All right. So okay. Sorry, I had to pull up the screen I was looking for. All right, so there we go. Can everybody see my practice problem? Should say 2.5 transformations. Can everybody see that? Hello? Did I lose everybody? Oh, there's still people. All right, well, everybody's staring. So anyway, this is an x squared function. It's going to ask us two questions. First, it's going to ask us to describe what's happening. Then we are going to actually have to graph the function. So this is kind of like what your homework is going to look like. So this is saying, what is yx plus 7 quantity squared? So this is asking us, what are we doing? So this is starting with a typical squared function, and that plus 7 is going to shift it which direction? So it's inside the function, so that's going to shift it left or right. And the fact that it's a plus means it's going to shift it to the left. So that's going to be this function here, this b1. So we're not shifting to the right, we're not shifting up, we're not shifting down. This plus 7 is shifting us to the left. So we're shifting a typical x squared function 7 units to the left. That's what it's asking us. Okay, and they want us to graph it now. I'm going to zoom this in just a little bit. Okay. Now, the good news is when it comes to graphing these functions, it makes it really easy on you. The v is an absolute value. The u looking shape is your x squared. This kind of curve is your x cubed. And that's all they're going to mess with. Other than that, it would be a matching. So if you're actually having to graph something, it'll only be one of these 3 functions. This is an x squared, so it's going to be the u-shaped graph. So you click on it with your mouse. And when you click on the graph, it just draws it right here in the middle. And then we're just going to do the shift that we said. So we're going to grab it and we're going to shift it 7 units to the left. So that's this gray box here. So horizontal shift. Okay. Vertical shift would move it up and down. We don't want to move it up and down. Horizontal shift is what moves it left and right. And we want to shift it to the left 7 units. You can see where it says kind of that -7 here. You can see the numbers kind of counting down, 4, 5, 6, 7. So we want to shift left 7 units. And again, that's kind of what your homework is looking for on a problem like this.
Okay, so that one is just taking a small piece of that value.
Correct.
And it'll probably lead up to being all complicated.
Actually, this one does a pretty good job of not getting too complicated, but they will do like multiple things. So for example, I don't know, it's so small. Hope you guys can see this. That says g of x equals -5 square roots of x. Okay, so it takes an initial square root function. Then, okay, we're multiplying it by -5. So that's actually going to cause it to stretch. Okay, the bigger the number, 5 is a big number. 5 is going to stretch it. Okay, by multiplying your y's by 5. Okay, remember, anytime you stretch, you're multiplying your y values by whatever the heck your number is. And then the negative is going to take it and flip it over the x axis.
Will the negative always flip it?
Yeah, always. And it always flips it over the x. Your a value will always stretch. If it's a fraction, it'll shrink it. If it's a whole number, it'll stretch it. It always multiplies to the y. And if it's negative, that's going to flip it over the x-axis. So any a multiplier will do those same things. The negative flips it over the x-axis, and a fraction will shrink it. Yep. No, I want you to ask them, because if you ask them, I reiterate it, and guess what? Now it's on the video for you to hear the answer as many times as you want to hear it. So anytime you have a question, ask it. Ask it, ask it, ask it. Okay, this wants us to match it. So again, the square root function typically went, up and to the right. So this one, we want to stretch it and flip over the x axis. So again, this one stretched it, but this is the one here, B, that actually flips it over the x-axis too. Because if you remember, the original square root function kind of comes up here and goes to the right. So when you flip it, that's what's causing it to come down and to the right. It's pretty much just like the example I showed right before we came to the computer screen.
Would Desmos help us at all?
Definitely. You could type these functions straight into Desmos and it'll graph it for you 100%. Yep. Just you can't use Desmos on your test. But for homework, 100%. But that's the kind of questions it's going to ask within 2.5, and that's really all it is. So they can change functions. So really, as long as you kind of have an understanding of the parent function, you're good to go. So x squared makes a u. X cubed does this number. Square root of x does that. I guess technically should include those as well. This is just your parent function. So if f of x equals this guy, this is what we would call the parent functions. So this is your basic graphs if no changes have happened. And then we should be able to take any of these and then do any and all said changes. A cubed root of x does this number. Absolute value makes a v, and a rational function. We'll do that right there. So that is your parent function. And again, for your test, I'm going to do one of those, one of those, and one of those. Your homework could potentially touch on all of these. These are the ones that you'll have to do. And again, the parameter changes are all the same regardless of whatever function we're talking about. So if I said f of x is negative cube root of x plus 1, okay, that's going to take our cube root of x function. The negative is going to flip it vertically. And then this plus 1, again, inside of the radical is going to shift us left 1 unit. So this is going to flip. And this is going to make us go left 1. So from that same cube root function, cube root, we would flip the thing over and then shift it left 1. So instead of, so again, if that's your original function, we want to flip it. We want to go left 1. So it's going to go kind of like that. So this is the original function. This one is flipped and shifted left 1 unit. So regardless of what function we're talking about, x squared, x cubed, square root of x, rational, cube root, square root, the parameter changes whether it flips or stretches or shifts left to right or shifts up or down is all the same. Just the picture changes based off of which function we're dealing with. Okay, so if we have a multiplier of 3, absolute value, so that's going to be this V-shaped graph. This plus 4 is outside, so this is going to stretch by a factor of 3. And then this is going to shift the whole thing up 4 units. I didn't do a good job of graphing that, but it's typically going over 1 and up 1. So the original y equals square root of x function starts at 0, 0, and goes up 1 over 1. Okay, kind of like so. So that would be your original absolute value. And again, this one's going to shift the whole thing. Every single point, it's going to go up 4 units. And then your y values are going to multiply by 3. So that means you're going to take this and you're going to triple each of those y values. So you get a much skinnier, more vertical graph. So each point gets shifted up what would be 4 units and you're multiplying it by 3. So instead of going over 1 and up 1, you would go over 1 and up 3. So each time you would go up an additional 3 units. So like so. So again, that multiplier stretches the graph vertically. And again, that's based off of the original function. So there's a typical square root function, regular v, up 1 and over 1. So multiplying it by 3 stretches it, makes it really skinny. Okay, it gets vertical really fast, 3 times as fast. And then the plus 4 just moves the whole thing up 4 units. And I didn't really show a shrinking one, so if I said f of x equals 1/2 of x, so again, this is your typical absolute value, starts at 0, 0, goes up 1 over 1. So this is regular. If we cut all of those y values in half, so again, this is your multiplier. To be in a fraction like that, this is going to shrink the graph. Basically, you're cutting your y values by this multiplier. So you're still multiplying. If you take 1 and multiply it by a half, half of 1 is a half. Half of 2 is 1. Half of 3 would be 1.5. Okay? So we get this flatter, wider v. So again, when you multiply it by a half, you're essentially shrinking your y values down. This one would actually be better if I would have drawn it on a separate one. No, the x values don't change. So as you move horizontally, the multiplier affects what your y is doing. So for each horizontal x value, you're cutting your y values in half, and that's making it a much flatter graph. So you're still going over 1, just now instead of going up 1 full unit, you're only going up half of that. I'm doing such a terrible job of graphing. If I go this is Desmos. Hopefully you're seeing that. Again, DESMOS.com. It's a graphing calculator. And it'll graph anything. You can literally type in whatever the heck function you want and it'll graph it. So this is your typical absolute value function. And if we cut that in half, that literally cuts all of my y values in half. So y value of 1, y value of 1/2, y value of 2, y value of 1, y value of 4, y value of 2. It cuts everything in half. If we took that same thing and made it a 3, taking all those y values and tripling them, so they become way more vertical. Okay, and the bigger the number, the skinnier that graph is going to stretch. Desmos does a way better job of showing you all the different things you can do. And again, if we took that and made it negative, that's going to flip it over. If you add a number inside, that shifts it left. If you add a number outside, that's going to shift that up. So this would go left 3, up 1, flipped over. So that's what each of those values do. And you could do that for any of those functions. So if we did a cubic function, okay, there's your cubed. So the negative flips everything over. The +1 moves everything up 1 unit. The +3 shifts everything left. So this particular point, 0, 0, okay, goes up 1, left 3, and then it flips the graph over. So instead of going up and to the right, now we're coming down and to the right. So the negative flips your graph. Everything else shifts. So this point here at 1, 1, we're going to shift left 3. So 1, 2, 3. Okay, up 1, but then it flips. So that's where it's going down to. Desmos does a great job of quite literally illustrating exactly what the graphs are. Plus, it's easier to differentiate because of color. It's like, there's my initial function. Okay, this is my transformed function. that's all we got. So again, next time we are going to test you guys who are not here in Lebanon. You don't need to sit here and watch us take a test. You are supposed to test on your own. So whenever you test, that counts as your class time. So your attendance is going to be recorded based off of you completing your test. So we're not going to make a Zoom for you to watch us test. So again, next week, set up a time where you can Zoom into your, not Zoom, set up a time where you can go to your proctored site. Okay, and then make sure you're taking your test. That's going to be your thing. So that's what I got. Okay. All right. See you guys.